We are joined by a wonderful presenter tonight, Abby Bault. Abby is a postdoctoral fellow at the physics division at Berkeley Lab up the hill. She's a member of the Dark Energy Spectroscopic Instruments collaboration, where they are working to construct the largest 3D map of the universe, looking back from today to 11 billion years ago. Desi, her research focuses on astronomical instrumentation and high redshift cosmology. She gets to work hands-on with the focal plane and spectrographs, two systems that work together to collect data to form the map of the universe. And she also studies the conditions of the universe as it was when it was only a few billion years old. Outside of the academic world, she enjoys crochet, weightlifting, and is an avid Detroit sports fan. Take it away, Abby. Thank you.
Great, thank you, everyone. So I'm very excited to be here today, and thank you for that wonderful introduction. Before we get into the nitty-gritty, I want to just go through a little bit more about myself, just so that you know sort of who I am. So as was mentioned, my name is Abby, and I have a postdoc in the physics division at Berkeley Lab, just up the hill. I actually just started at the lab in September because just this past summer, I received my PhD from UC Irvine in physics. So yes, you can call me doctor. Prior to that, I did my undergrad studies at Wayne State in Detroit, where I'm from, and that's where I'm originally from. Yeah. So as was mentioned, because of that, I'm a huge Detroit sports fan, specifically hockey with the Red Wings. Yeah. Okay, find me later, because we're not here to talk about sports right now, unfortunately, even though I would love to. So if you want to, please find me later. Hockey or football, any of them, let me know. So tonight we're here to talk about astronomy. So at Berkeley Labs, my primary focus is on astronomical instrumentation. So that means that I work with instruments that we use in astronomy to collect the data that we're using to study the universe. So I get to work hands-on with these instruments, and I get to work with the focal plane for the dark energy spectroscopic instrument with these tiny little robots that are being used to collect this light. And I'm also starting to work with the spectrographs, which are basically just giant digital cameras in a sense. Digital cameras. So tonight I'm here to tell you sort of what we do with that data. So I'm also a cosmologist, which is a type of astronomer, but I study the universe as a whole. Press what? Oh, crud. Okay. The mouse doesn't show up on that screen, so we might have to live with it. It's all good. Yeah, the mouse doesn't show up here for some reason. Okay, yeah, unfortunately, it should be fine. So I'm a cosmologist, which is a type of astronomer, and I get to study the universe as a whole. So I study what the universe is made of, how it is organized, and how it has and will evolve. And tonight I'm here to tell you that the first question, what our universe is made of, is still a mystery. And we don't know. So full disclosure at this point, these slides are made by my colleague, Allison Bronzeller. She was actually supposed to be here tonight giving this presentation to you, but she had a personal emergency. So if you were looking forward to hearing her talk, I am sorry you are stuck with me. So I said we don't know what our universe is made of, and that might be quite alarming. It is actually just a bit of an exaggeration. The truth is, we don't know what 95% of our universe is made of. This may do little to comfort you, because while it's something, it's still quite alarming. So don't panic. If you've never heard this before, you might be feeling a little bit skeptical, and rightfully so. The statement doesn't really fit that nicely into many people's lived experiences and perceptions of the universe, right? What you see is what exists. You may have arrived here today either by transit or in a car. And I bet that you're fairly certain that your car was made of matter. You might even be able to get more specific on exactly what type of matter. So cars are made mostly of steel, aluminum, and plastics. Some of you might even have a water bottle in front of you, like this one that I have here. And I would bet that you are fairly confident that this water bottle is also made of solid matter. You feel it, you touch it, you see it. You might even deduce that the water bottle is made from the same material as a typical car, meaning steel, aluminum, and plastic. I think this one is some type of wood. You can even break these ingredients for cars and water bottles down even further to understand what these objects are made from at a molecular level. For example, plastics are just a different combination of carbon, hydrogen, oxygen, nitrogen, sulfur, and chlorine. The full collection of fundamental elements conveniently organized here into the periodic table make up every object that we interact with in our daily lives. And that includes our own bodies. We breathe in oxygen. Oxygen makes up our body. We also have carbon, hydrogen, nitrogen, and some various other fundamental elements. So if everything we interact with is made of these elements, then we must know what our universe is made of, right? I mean, it would make sense. Now, I put an asterisk next to everything because all of us are interacting with both gravity and light as I speak, but both of those are not made from elements in the periodic table. These two things, however, are not part of the mysterious 95% that we don't know. We actually understand both gravity and light quite well, thanks in big part to this guy, Albert Einstein. And it's actually by studying the light from distant objects and from using Einstein's theory of gravity that we know there is more to our universe than meets the eye. So to make sure that everyone is sort of on the same playing field here with gravity, let's go through a very brief crash course and go through it. So gravity is the force that not only is keeping you in your seat right now, and I'm not going to do it, but if I was to let this water bottle go, it would fall to the floor. It is also what keeps the moon in orbit around the Earth, and it keeps our Earth in orbit around the sun. And the more massive an object is, the stronger its influence will be on nearby objects that are orbiting it. And so what that means is that the speed of that object orbiting is going to depend on that central mass inferior to the orbit and how far out that object is orbiting from the radius. If that central object has more interior mass, so it's larger, then your object orbiting is going to orbit that object faster. But if you're at a further and further distance away, you're going to move slower. That object is going to orbit a lot slower. So we can actually see this behavior in our very own solar system. Most of the mass in our solar system is contained in the sun. That is the most massive object in our solar system. And we see that planets that are further from the sun actually orbit slower than those that are closer to the sun. So we see that the mass interior to the orbit of Neptune is essentially equal to the mass interior to the Earth's orbit, which is just roughly the mass of the sun. And because of that, we see this drop in orbital speed as we get to the outer planets in our solar system. So the closest planet to our sun, Mercury, that's actually orbiting the sun at roughly 50 kilometers per second. Now, that is the metric system, right? We use the imperial system. So if you're curious as to how fast that is, 50 kilometers per second is roughly 111,000 miles per hour. That's very fast. And then as we get further and further away from the sun, things slow down. I don't have that conversion off the top of my head, but it's still much faster than you could ever get your car to go. We can also extrapolate this expectation for orbital speeds to the scale of galaxies. So if we assume that the mass in a galaxy is where all the luminous matter is, meaning everything we can see, gas, dust, stars, we can predict the orbital speed of matter at different distances from the center of the galaxy, or the galactic center. And so what we'll expect is that the orbital speed will first rise as we go through this distance, because more and more matter is at the center, near the center of that galaxy. And then as we get further and further from the center, that speed is going to drop off with increasing distance from the center. But that is not actually what we observe at all. Even though there's apparently very little luminous matter way out here, far away from the center of that galaxy, what we see is that as you get further and further away, that orbital speed is actually increasing. And this is not at all expected. We expect the orbital speeds, like I said, to increase as you're closer to the center and then drop off. And so what is causing that? This leads us to the conclusion that there must be a lot more matter interacting in this galaxy than just what is interacting with the light, right? There's something here that we can't see. And we've given this unseen matter, we've called it dark matter. A little spooky, we're just after Halloween, quite thin. And so we don't know very much about dark matter, but thanks in part to astronomers like Vera Rubin and her study of orbital speeds of galaxies back in the 1960s, we have learned that this dark matter is roughly 5 times more abundant than all luminous matter. And right, so 5 times more abundant than everything we can see in our universe with our own eyes. But we still don't actually know what it really is. It's possible that we just don't understand gravity as well as we thought. It's quite complicated. If you've ever looked at Einstein's theory of gravity, there's a whole lot of math involved. So I think that's a fair statement that we don't understand possibly what's going on. Or maybe there's just a lot of really faint matter in galaxies that we're just missing. That's also possible, right? Our instruments that we create, that we have here on Earth, a lot of times they struggle to see really faint objects in our universe because that light can't get through our atmosphere. But even still, with some space-based instruments that don't have that problem, sometimes you just can't see those really, really faint objects that are really far away. Or it's possible that we have a fundamental flaw in our standard model for particle physics, and that the model is just incorrect. And maybe this dark matter is pointing to the fact that there's some interesting physics that we just haven't figured out yet. So these are a lot of questions that we ask ourselves on the daily. We're fairly confident that it's probably not number 2, but we haven't quite ruled that out yet. So sort of leaves us with the options of, well, either we don't understand gravity or our model is just incorrect. But what we now know is that dark matter and our regular matter, so everything that we can see, make up roughly 30% of the energy content in our universe. But that means we're still missing the biggest piece to the puzzle. Over 70% of our universe, we don't know what it is. And in order to figure that out, we need to zoom out a lot to find the remaining 70%. And so we need to zoom out to scales much larger than single galaxies in order to see this. In fact, we need to zoom out to scales to see multiple galaxies on the same scale. And so what we see when we do this, when we zoom out this far, we observe the apparent motion of galaxies in our universe, and we see a very interesting trend. What we see is that all galaxies, with the exception of those closest to us, are moving away from us. And in fact, not only do they appear to be moving away from us, but the further a galaxy is from us, the faster it's moving away. And this is true from any point in our universe, not just from our own local viewpoint. So all galaxies, you pick one, all other galaxies are moving away from it, and the ones that are further away are moving away faster. And because of this, the space between all galaxies is getting bigger. Similar to if you've ever baked like a fruit cake or a type of bread, like a banana bread with like, what's the word? What do I want? Nuts. Like, yeah, nuts. There you go. Thank you. When you pour your batter into the tin, right, everything is sort of close together, it's quite dense. And as you put it into the oven, it bakes and it expands, right? And you get a really nice distribution of fruit if you've done your recipe correctly. And so that same thing is sort of happening with space. This tells us that our universe is actually expanding, right? Our galaxies, these little clumps of fruit or the nuts in our banana bread are expanding and moving away from each other. And that's quite interesting that the universe is expanding. And in fact, not only is it expanding, but it's actually accelerating. And so in 1998, a little while ago now, 2 independent groups of astronomers, one actually from Berkeley Lab, found that distant supernovae are just stars that have exploded, right? They've had so much energy that they exploded. And they're very bright. So they found that these distant supernovae were actually a lot fainter than we would expect them to be with a constant expansion rate. So if the expansion just stayed constant. But because they're fainter, that tells us that the universe is actually accelerating in its expansion. And this discovery implied that the universe is expanding faster today than it did in the past. And that this apparently empty space between galaxies isn't really empty at all. It might look empty, but there is something there. There's some energy there. And this energy is strong enough to drive galaxies apart on large scales at an accelerated rate. And this is what astronomers have called dark energy. Now, this is not actually a really great name at all. So we call dark matter because we know there's matter there and we can't see it. So we've called it dark matter. It doesn't interact with or give off light. And I don't really know why dark energy got its name. I don't know if we picked it. But I think it's possibly because maybe it just sounds a little bit mysterious. Right? We don't know what dark matter is. So let's call this other thing that we don't know about, this energy, dark energy. Makes sense, I guess, but I'm sure we could have got a better name if we really tried. But we've called it dark energy, and so now we know the final piece of the puzzle to our universe. We know that we have roughly 5% of visible matter that we can see with our eyes. We have roughly 25% dark matter, and then the rest of it, the 70%, is dark energy. And so what exactly makes up these two dark matter, the dark matter and the dark energy, are two of the greatest questions today in modern science. We know that dark matter and dark energy are there, but we still need to figure out exactly what they are. And so it's the question of dark energy that I, along with many other astronomers, are currently working on. So as was mentioned, I'm a part of the Dark Energy Spectroscopic Instrument Collaboration, or DESI for short. So the DESI instrument is installed on the Bault telescope on Kitt Peak in Arizona. Unfortunately, I've never actually been there, but I've heard it's very nice. So the Bault telescope is this dome here with the shining silver top, and the DESI instrument sits at the top of the dome inside of it. Every clear night, DESI looks toward the sky and collects lights from tens of thousands of galaxies. And over its 5-year planned main survey duration, DESI will observe roughly 40 million galaxies in total. With these observations, we plan to build the most detailed map of the universe ever created. In fact, we kind of already have. So just in the first 6 months of DESI operations in the main survey, this is all the data we've collected. Now, it doesn't look like that much, but that is millions and millions of galaxies just in the first 6 months. And every point you see here is a real galaxy that we measured with DESI. And we're not finished yet. Now, light has a finite speed, which means that it takes time for the light from these distant objects to reach DESI and be observed. So when DESI observes galaxies that are, say, roughly 1 billion light years away, that means we are observing the universe as it was 1 billion years ago, because it took the light that long to reach us. And DESI is so powerful that it can see galaxies from when the universe was only a few billion years old. So the edge of the map here shows galaxies in the universe as it was roughly 10 billion years ago. So in essence, we're effectively using DESI as a time machine, right? Everyone's always trying to create time machines, and we kind of have. So by looking at snapshots of the universe at several different points in its history, we can better understand how dark energy, and actually dark matter too, is affecting and is influencing the evolution of our universe. And this will help us gain a more complete understanding of the properties of dark energy and get us closer to solving the mystery of what dark energy is. Now, I showed this plot from just the first 6 months of DESI data, but actually, probably hopefully pretty soon, are the results of our year 1 data will come. And in year 1, we observed even more galaxies. And so I have a special fly through, hopefully it plays. Oh, I need to get the notes up here. Yeah, I'll show that. So this is from our planetarium show that we created in DESI. So if you want to look at that, there is a version on YouTube. It's about 20 minutes long. If you just Google DESI planetarium show, it will pop up. But this is going to show a fly-through of the data we collected during the first year of our survey. And it takes a little bit in the intro. So every single one of these points here that you see on the screen is a galaxy that DESI collected light from, that we observed with our instrument. And we created this fly-through of where they live in the universe. So we'll just take a couple minutes and watch it because I think it's really cool.
Is the Milky Way galaxy behind us in this fly through?
That's a good question. I think this would be from our point of view. So usually when we observe, we try to avoid the edge, the Milky Way is a galaxy like this. We try to sort of avoid looking directly into the edge of it, because there's actually a lot of gas and dust there that will block us from seeing the other galaxies. Pretty sure this is from the point of view of us. So we wouldn't actually see the Milky Way as such as galaxy.
So it would be above and below the plane of the ecliptic.
Yes, thank you, yes, it's the word I was looking for. So every single one of these points that you see is a galaxy that we were able to obtain.
You know how far away they are.
Yeah, so that we know, we measure what's called the redshift of the galaxy. And so for that, we split this light that we collect from DESI into sort of wavelength constituents. And when we do that, you see either these emission lines or these absorption lines of different elements. And that allows you every element has this unique sort of fingerprint-like structure in its emission and absorption lines. And if you know where those are in the rest frame of the wavelengths, so where it would be now, you can do this sort of redshift technique, which will tell you how far it is. Because maybe that line pops up at a different wavelength versus where it should be at rest. And so that tells you exactly how far away these galaxies are. And then you can do a little bit of math and get an actual distance with it.
Those are false color images, right?
Yeah. So I don't actually know how long this plays for, so I'm gonna move it on. So our current understanding of how dark energy fits into our model of the universe has always been that it's a constant, meaning it's the same today as it was a billion years ago. However, the first year of DESI data that I showed you has slightly contradicted this.
So what?
Contradicted. Now, I say slightly because the change is so small that it hasn't been statistically confirmed yet. We actually need a bit more data to do that. But this deviation starts roughly 8 billion years ago when galaxies were actively forming and becomes the strongest at about 3 billion years ago, roughly when the expansion of the universe began accelerating. And so this deviation that I'm talking about is this dashed line from that solid black line. And so our full 5-year DESI survey will either confirm or deny this result. But either way, it's going to be very exciting because we thought, since dark energy was thought of, we've always assumed that it's just constant. And it turns out it might not be. But unfortunately, we have to wait at least 2 more years to finish collecting all the data. And then realistically longer, but at least another year after that to do the analysis. So we have to be very patient. But in the meantime, maybe dark energy is constant, maybe it's not. So unfortunately, we haven't answered any of the questions about the universe. In fact, we've added one instead, so now we have more things that we need to answer. Because if dark energy isn't constant with time, what is it? We don't know. So yeah, we don't know what 95% of our universe is made of, and we've added more questions to the puzzle that we need to figure out. But one day we will figure it out. And maybe that'll be in a couple years when DESI is done, or maybe it'll be with the next generation of instruments. Stay tuned.